the stereoisomer part, which is a small, tiny portion, and then effectively go through almost everything, every topics in Arkin. So we won't have class on Wednesday. Okay, so you guys can make a plan accordingly. If we cannot finish the Arkin stuff today, then I'll know the recorded lecture for the relevant part, so that you can study by yourself with the recorded lectures. Okay. So again, we won't have class on Wednesday. Okay. And this Saturday we'll have midterm. Right? I will notify the details about the midterm on ETL, so you guys can check the notification. Okay. So I'll notify the location for the exam and time. And you guys should also bring your homework. Okay. Set the sole homework set in hard copy. Okay. And submit to the proctor and TA before the exam starts. 질문 있는 사람? 없으면 오늘 조금 efficient하게 진도를 나가보도록 하겠습니다. Right, so I guess we stopped here last time. We deal with what is the optically inactive and active means though, right? So enantiomers have identical chemical and physical properties except in their interaction with chiral species, chiral substances, or the polarized light, the plane polarized light. So we discussed what is the plane polarized light, right? From the light source, we can generate, right? Light source gives you the normal light, which has the all direction, right? But after going through the polarizer, your normal light will have the plane polarized light. So you can think about the polarizer as kind of like slit, okay? What you can get the plane polarized light. And if you have some molecule, the sample, right? And if this polarized light goes through the sample, then depending upon the nature of the molecule or sample, this polarized light gives you a different pattern. Right? So plane polarized light is a light that has an electric vector that oscillates in a single plane. Okay? And polarimeter, this is what you're going to use for the experimental course, which allows to measure the degree to which the organic compound rotate the polarized light, right? So after going through, right, the sample, the molecule, this plane polarized light will show you some rotation, right? And you can measure that using this instrument, the polarimeter. Okay? And the rotation angle is giving you some sense of like periods of your compound, target compound, right? Or mixture, how much, right? R versus S forms are mixed. For that, I guess, yeah, this is sort of like the schematics of what happened after the polarized light go through the sample with the achiral compound versus chiral compound. Achiral compound won't give you any rotation, right? Achiral compound doesn't have any specific interaction with the polarized light, right? So that's why the plane polarized light, they doesn't change, they remain intact. Whereas the sample with chiral compound start to interact with this polarized light will give you some rotation of the plane, and you can measure how much angle rotate, okay, using the polarimeter. So when you see the rotation, right, then we can say the compound is optically active, right? That's what that means. The sample or molecule in the sample chamber can rotate the plane of the polarized light, giving you a specific angle, alpha. Whereas achiral compound is called optically inactive, doesn't give you any rotation. Okay? And this is the equation we studied last time. So you can measure again the alpha value, right, using the polarimeter. And you can normalize that, right, with the length scale and concentration of the sample, the molecule in the sample, right? So you can imagine there's a sample chamber that looks like this. It's a length scale L, right, and concentration C. So if you normalize the measured alpha value with these, right, the length scale times concentration, then you are getting something like the normalized angle. Right? That's how you can normalize, right, all of the rotation values. And then you can compare, right? That is called, by the way, the specific rotation. A specific rotation of a pure sample, for instance, will give you the following numbers. So 2-methyl-1-butanol is a pure R form, will give you plus 5.75 degree. Right? That's the rotation, normalized rotation you can get. You have 100% of these R molecule, whereas you have S molecule, right? The enantiomer, then this will give you the same magnitude but different minus. In this case, the plus minus sign will get improved, right? So you're getting minus 5.75 degree, right? If you have 100% of S. But you can think about the case where R and S forms are mixed, right? And your sample, right, have a mixture of these two. And still, this can give you some number rotation, unless these two are 1-to-1, exactly 1-to-1 ratio. Right? So from the raw measure value and comparing that with the specific rotation, right, then you can get a sense of the purity of your sample, right? How much R form exists or how much S form exists, right? So you can compare the measured optical rotation from the sample you have and specific rotation that pure R or S form would give you, right? Then from these two, you can get a ratio of the two enantiomers. In other words, you can get a sense of the purity of one over the other. Okay? In this context, you can define the enantiomer axis, right? It's simply, right, the excess amount. This is delta, the difference, right? Which can be defined as a magnitude of one, right, minus the other. S minus R or R minus S, right? And you can get a sort of like quantitative sense from the exemplary statement below, right? You have the rotation value, right, of 40% EE of S2-bromobutane, right? That is 23.1, right? And then you can think about then, right, specific rotation, right? So you can take a look at this equation. The enantiomeric axis can be defined as the observed specific rotation, right, divided by the specific rotation of the pure enantiomer, right? And if you can get the percentile of that value, then it will become the enantiomeric axis. Okay. For example, if the sample of 2-bromobutane has an observed specific rotation of 9.2, right? And you can simply divide it 9.2 by this value, the pure value, right? Then this will give you 40%, right? That's how you can match, right? The enantiomer axis and the ratio you got following the equation. Okay? So enantiomer axis tells it how much excess in one enantiomer in a mixture. Okay? So you can then maybe make a very simple equation, right? Here, S minus R is 40%, right? And we know that S plus R has to be 100%. Okay? Then from this, you can get, right, S has to be 70% and R has to be 30%, right? So you can do simple math like this. Okay. What about the S-butanol has 6% EE, right? And you can get a simple math again, right? S minus R is 60%, and you know that S plus R is 100%. And S should be 80%, right? And R should be 20%, right? What you can match the enantiomer ratio. Right? Enantiomer ratio, 80% here in this particular case, indicates the ratio of the percent of the one enantiomer in the mixture to that of the other, right? So 80% sum present the enantiomer axis in this case. That's how you can differentiate the enantiomer axis and enantiomer ratio. Okay. Optical rotation, you can think about a little bit more. This again can be measured with the colorimeter. And here's the notation, right? Plus D minus L plus minus DL, right? You have the racemate, or in other words, racemate mixture of two enantiomers, then you can follow this plus minus notation or TL notation, right? But you should note that there's no relationship between absolute configuration and the plus minus sign here, right? So some R enantiomers can give you plus, and some can give you minus, right? There's no absolute relationship between, right, absolute configuration and plus minus, right? Notation, right? It's all molecule dependent, molecule specific. Okay. A chiral compound rotate plane polarization, right? You know, if it rotate plane clockwise, right, then you can put a plus sign. If it rotate counterclockwise, then you can put minus sign. And D stand for the depth rotation, right? And L here is the lab rotation, right? So plus minus DL, right? That's the notation you can follow. But again, there's no relationship between absolute configuration and plus minus. 그래서 지난 시간에 이야기한 겁니다. 일단은 플로리미터에 넣고 샘플을 넣고 측정을 해보면 뭐 시계 방향이든 반시계 방향이든 돌아가겠죠. 시계 방향으로 돌아갈 때 플러스 T로 표기를 하고 마이너스 방향으로 카운터 클락와이즈 반시계 방향으로 돌아가게 되면 마이너스 N으로 이제 노트는 할 수 있는데 이제 뭐 R폼이라고 항상 그러면은 시계 방향이냐 그렇지 않다는 얘기예요. 분자 스페시픽한 것이기 때문에 기계적으로 뭐 R폼이니까 항상 플러스다 이렇게 할 수 없어. 이해가 있다. Right? We can think about the physical properties of the stereoisomers a little bit more, and we can here first think about. We can define the racemate mixture. Racemate, as you know, it's a mixture of equal now, 1-to-1 ratio of two enantiomers. Right? In that case, you can say it's a mixture. It's a racemate mixture. Right? In short, you can say racemate. Okay? And you can expect that racemate mixture is optically netted. The rotation get cancelled. Right? So net rotation has to be 0. And table 5.1 summarize, right, the physical properties of the enantiomer given enantiomer A and B, right? And then there are some comparison. And here's the properties: melting point, boiling point, optical rotation. These are right physical properties. A alone, B alone, right? They will be identical to each other. Okay? There's no difference in physical properties. But what about the optical rotation? Here in A alone versus B alone, they will show you the equal magnitude, right? But opposite side to each other, right? What about racemate? Racemate mixture A plus B. Their melting and boiling point, the physical properties, they can be different, maybe different from A and B. Okay. Optical rotation will give you 0 in all cases. Right? The rotation should get cancelled. A can give you, for instance, like clockwise, right, rotation. Then B can should give you, right, the counterclockwise, and they will get cancelled to each other. That's why you're getting 0 degree in all cases. Right? The physical properties, they can be unique, right? They can be different from A or B. This is a specific example of the molecule, right? And let me see. Yes, it's enantiomer have identical physical properties. They cannot be separated, right? They have same melting point, boiling point, right? And solubilities is also identical. So they cannot be separated by common physical techniques. Okay. What about diisomers, right? Diisomers are and conscious isomers. They have to have different physical properties. So in theory, you can separate, right? To diisomers. So take example here, you have A, B, C molecule. Okay? A and B, they are enantiomer to each other. But A and C and B and C, they are the diastereomer relationship, right? That means you can separate B out of C or A out of C, right? And here's the properties. The specific values are given: melting point, solubility, right, and optical designation here. A and B you see closely, right? Melting and solubility, they are identical. C has different numbers, the melting point and solubilities. What about racemate, the racemic mixture? This will give you also different numbers, different from A, B, and C, right? It's a unique numbers. What about the optical properties, right? The specific rotation, A, give you the same magnitude, but an opposite, right, sign with B. C and racemate, they will give you 0, right? C is not optically active, right? Racemate also not optically active in this case. And you can compare RS and D designation as well. The particular properties A and B differ from their diastereomer. C, the particular properties of racemate A and B can also differ from either enantiomer and diastereomer. C, the A chiral major compound, right? That's why it won't give you any specific rotation, right? You look carefully as an internal symmetric plane, it's a major compound. That's why this gives you 0 rotation. It's an A chiral compound, right? Not because it's a diastereomer to A or B, but because this is a major compound, that's why you're getting 0, right, degree. Another specific example, so you can take a look and compare, right, the physical properties, optical properties, right, and solubilities, of course. How can you separate stereoisomer percent, right? Let's say you have the enantiomers in a mixture, and you want to separate them, right? There are some ways, like the primitive way, there are mechanical separation of tartrate. This is one example how mechanically you can separate. Basically, you can crystal out, right, and just separate one by one by using pinset. So, R foam, S foam, their crystal structure or crystal solid has a different directionalities. So by seeing your eye, right, you can pinpoint, right, R versus S. That's how you can separate, right? Sounds quite inconvenient. There's another way you can make a reaction, right? You have R and S mixture, right? Racemic, and you can react this with, for instance, like one specific, right? The enantiomer molecule. For instance, in this case, you have R foam, right, for this reactant. So since this has amine here and you have acid here, you can expect some acid-base chemistry can occur, right, to formulate some salt, right? And these two have some specific interaction, right? And in this case, then you can call out R salt. You're using R acid and R amine, right? But this can also react with the S form, right? And this will give you SR salt, right? As a result, now you can think about these two. They are in diastereomer relationship. Must have different physical properties, right? So you can separate one salt out of the other salt, and then you can remove the amine, then you can get, right, R and S form, right, separate. 그래서 뭐 racemic mixture가 있다, R폼, S폼이 있대, 1대1로 섞여 있는 거잖아요, 그렇죠? 그러면은 무언가 방향성 있는 물질과 반응을 시킨다. 옵티컬 액티비티 이야기할 때도 이렇게 이제 polarized lines 썼던 방향성 있는 substance라고 우리가 생각할 수 있겠죠. 빛과 반응하게 되는 그 정도가 다르고, 여기서는 이제 다른 이제 예를 들어서 R폼인 아민을 쓰게 되면 acid base 반응이라서 RRRS4 이렇게 생기게 되면 다이스로 관계에 있게 되기 때문에 이 둘의 이제 simple property 차이를 이용해서 separation 할 수 있게 된다라는 이야기. 같은 맥락에서 이해해 주시면 되겠고, yeah, and this is a detailed sequence, but basically same procedures next case, we have the racemate. You can react with, right, the molecule, in this case B. So A and B, they react, and this will be the diacetyl, right? And you can separate by its group properties. And then reverse the reaction, you will get R and S form and separate method. This is detailed procedures. You need to know the detail. You can understand that principle. So after forming, right, the salt, you can maybe utilize different solubilities, right? Different physical properties will allow you to separate the one from the other. Okay? And you can think about the properties of the enantiomer, right? And then biological settings, biological system, right? Chiral agent, the drug, right? And an active drug, they all have the, basically they are pure enantiomer form. And the reason for that is the receptor in your body, in your cell, it's a very specific interaction with the chiral molecule, right? That's why the drug or the bioactive molecule, they are, in most cases, very chiral. Two enantiomer have exactly the same chemical property except for their reaction with chiral, the non-Rust region. Right? This is the general statement. The enantiomer, they do have different reaction, right? With different sensitivity towards the chiral substance, right? Or chiral region in this case. And many drugs are chiral and often must react with a chiral receptor or chiral enzymatic sites to be effective. That's how, right, the chiral molecule shows some effect, right, in biological settings as well. So 같은 맥락의 이야기죠. 카이랄 모lecule들이 결국 카이랄한 어떤 substance와 반응을 이제 유니크하게 하게 되는데 biological setting에서는 이제 receptor, 셀 구조 안에 있는 이제 receptor, 그 프로테인 구조 안에 receptor와도 이제 다르게 반응하죠. 그래서 특정 카이랄리티를 갖는 분자가 특정 효과를 가지고 있다. 그래서 바이오액티브한 분자들을 보면 다 대부분 카이랄 센터를 가지고 있죠. 카이랄한 분자들. Okay, that was about the chapter 4, right? And then we can move on to the arcene, right? So what is arcene? Arcene is a compound containing alcohol, right? So we'll discuss, right, structure, name, and maybe we can discuss a little bit about the reactivities and basics, very basics of thermodynamics and kinetics. That's the scope that we'll discuss in this chapter for arcene. So arcene, the simplest molecule is ethylene, right? It looks like this, right? And of course, arcanes, the main important roles in biology. The ethylene or ethane, in particular, is a plant hormone, right? They control growth and other changes in tissue, right? In plant's tissue. So basically, this ethylene, right? This is very important for the ripening process, right? For instance, for this fruit, right? So ethylene can come on the genes for enzyme synthesis, and this function in the fruit, right? They facilitate basically the degrading part, right, within the fruits. That's what ripening means. Right? So from getting ripe banana to the ripe. You need to get them. So very important, and you can find varieties of the arcane family, right? Many flavors, and also like the pheromones, right? They all are arcane. They contain arcane. Right? So in this chapter, we'll study arcane. Its structure, and if you know the structure, then you need to know how to call out, right? So name and structure, they are coupled. That's why we need to know how to call out, how to name the molecule, right? So we need to know the nomenclature for the arcane type molecule, and then what's that interaction. So general stuff about arcane. And maybe we should discuss first degree of the unsaturation, the DU, right? We need to be able to calculate the degree of unsaturation. This can guide you, right, with a given molecular formula, how many ring structure, how many double bond, how many triple bonds exist. Right? And here is the principle. So saturated form for the hydrocarbon follow this. carbon, n number of carbon with 2n plus 2 number of hydrogen. This will give you the saturated form, the saturated hydrocarbon like this, right? So that's right? CnH2n plus 2 general formula, right? Per minus 2 hydrogen, right? You are getting plus 1 du. Okay? So take an example here. You have minus 2, right? Hydrogen or this alkene, okay? In this case, you can calculate du equals 1. This is another case, right? Same molecular formula, still du is 1. Okay? So 1 du can correspond to either 1 pi bond or 1 ring structure in the molecule, right? So here you have 1 pi bond, right? You have 1 ring structure. That's how you can compute and calculate degree of saturation. What about this case, right? You have 1 ring structure and 1 pi bond, 1 double bond. So you can expect du must be 2, right? Then you can also expect, right, the molecular formula to be 2 more hydrogen has to be lost, right? So that's why you are here C5H8. Right? So hydrogen decreased from 12 to 10 to 8, right? This molecule, cyclic alkene, has a du of 2, right? And then you can analyze further. It has 1 ring, right, and 1 pi. Okay? You can generalize this to all molecular formula, basically. And then you can think about this case, C8H14, right? Then you can first compute, right, the number of hydrogen that will give you the saturated form, right? And you can do simple math, right? 2n plus 2. This will give you 18, right? But you have 14. That means du has to be 2. Right? To satisfy this number, right, you can think about all different possibilities. Right? You may have 2 double bonds, right, or 2 pi bonds, or you may have 1 ring structure and 1 pi bond, right? You can have 2 ring structure, okay? And in this case, you can also have 1 triple bond. Triple bond has 2 pi bonds, right? So you can count for 2. Right? Du of 2 with 1 triple. Right? Again, you can think about this saturated case, which follow this general formula, and then you can compare that with the unsaturated case. In this case, of course, du has to be 1. The saturated hydrocarbon have no double bond. Unsaturated hydrocarbon, they have 1 or more double bond. Right? That's what saturated versus unsaturated means. Saturated with hydrogen or unsaturated. Right? There are 2 hydrogen sites are unsaturated in this case. So that's what saturated versus unsaturated means. What is the molecular formula for each of the following? Right? You have 5 carbon, right? So you can start with C5, right? You have 1 pi and 1 ring. So what is the du then? Du has to be 2. And saturated case should be this, then you can minus 4. Right? So this will give you the correct molecular formula for A. You can do the same thing for B and C. So what we should do is compute the du with the given information. You have 2 pi bonds, no ring, so du has to be 2. Okay? What about C? You have 1 pi bond, right, and 2 ring, so du has to be 3. In this case, so you have then deduce 6 hydrogen from the saturated case, so 10 carbon, right? Saturated case has to be this, right? Then you have to deduce 6 from this. Will give you then, right? C10. hydrogen 16. 그렇죠? 그러니까 DU를 꼭 기억을 하시면 유용하실 겁니다. 그러니까 DU, degree of saturation인데 원리를 생각해 보시면 saturated case에서 수소 자리가 2개씩 비게 될 때마다 DU가 하나씩 올라간다 생각하시고 링이 되면은 카본이 옮겨야 되잖아요. 수소 자리가 2개가 없어져야 된단 말이에요. 파이본드가 하나 생기려면 이중결합이 생기면 수소자리 두 개가 없어져요. 그러니까 DU가 하나가 해당이 되겠죠. 그런 원리가 적용되는 겁니다. 단순 수학 산수니까 링 하나, 파이몬데 하나, DU가 매칭이 된다. 요것만 기억하시고 saturate 된 케이스는 무조건 CnH2n 플러스 2식을 따른다. 요것만 기억하시면 이제 조합 가능성을 다 확인해 줄 수 있겠죠. Another mass, right? Degree of saturation for compound, right? So you can do the mass. So you have 48, right? Then you have 38. That means DU has to be 5, right? 맞죠? 이런 문제는 뭐 그냥 저는 그죠. Alright, what about the nomenclature? So again, arcane is a double bond, right? So there must be another rule. So first of all, you should replace the A and E, to E and E. Right? So E here indicate you have arcane, right? The arcane functionalities, the structure. So for instance, you can think about the systematic name only here. You have the ethane moieties with arcane. That's why you call this ethene. Okay? And here you have propane architecture, but with the double bond, right? You can call out the propane, E and E, cyclohexene, cyclohexene, instead of cyclopentane, cyclohexane, or something like that. Okay? So you have arcane functionalities. And the functional group here, which indicated here, the double bond, right? Double bond site, should get the lowest possible number. Okay? That's the rule number one, the primary rule, right? So instead of like selecting the longest possible chain, you should pick the chain containing this function, right? So you should fix, you should undesignate, or you should have this, right? 7 carbon containing, right, chain, because you have to pick the chain that contains the key functional group, in this case arcane, right? That's why this is called out hexene at the end of the day. And then of course you can call out the substitute accordingly. So this is very important, right? This is a primary rule, okay? And this is already what we know, right? We learned about EG, right? Nomenclature. As the arcane, you should specify, right? E versus G if necessary. If you have 2 substituents other than hydrogen, perhaps then you can utilize cis versus trans. These are equal. But if you have more than 3 substituents, right? Then you should follow the EG nomenclature. Okay? There are some rules. What about diene? Diene means you have 2, right? Arcane site, right? 2 double bond. Of course, in this case you can call out diene, right? So you can count number of carbon, right? In the main chain has to contain, right? There's 2 arcane, of course. You cannot miss the key functional group functionalities. And you have 7 carbon containing, right, chain that has 2 double bond. And you have to pull out the starting carbon, right? The starting position of the double bond. So that's why you can start here from 1, right? And then you can assign the lowest possible number for, right, the starting carbon for the arcane for the double bond, which is 2 and 4. So you can put 2 and 4, right? And for your heptadiene. Okay? So this is starting from like the structure of the heptane, right? And from the heptane, you have to convert it to heptene, but you have 2, right, arcane site. That's why this is heptadiene. So for the diene, you have, and in this case, you have 3, right? Then you can put triene right at the end, and you can count the number of, right, carbon, right? Which is 6, right? So this is 1, 3, 5. Again, the starting carbon site of the double bond. 1, 3, 5 hexatriene. That's the name for this alkene. Okay? So this is what I already illustrated, right? Number the chain of direction that give the function group the lowest possible number, right? So in this case, you can identify this main chain, right? And then you have a choice from left to right or right to left, but you have to choose from left to right to give you the lowest possible number for the starting carbon of the double bond, right? So this is number 1 carbon, number 2 carbon, okay? And then you can identify number 4 carbon that has methyl substituent, right? Then in trim, you can put together, you can make the full name 4-methyl 2-pentene, okay? That's a full name. What about this? You can identify the longest possible chain containing the double bond. And then you have a choice from from left to right, right to left. But in this case, you have to choose this direction always. Okay? So that you can assign this carbon number 2. Sorry, this carbon number 3. You're starting point of the carbon for the alkene. Right? If you choose this direction, then you will get number 4 instead of 3. So this should be the right direction, and then you can put 3-methyl for the full name. 3-methyl, 3-hexane. That's a full name for that. What about this case? You should remember how you call out the epoxy. Sorry, the ether, right? So in this case, you have the main function group, which is alkene, right? And this is treated as a substituent, as a carboxy substituent, right? As we studied in the preceding chapter. Right? We learn how to call out the ether, right? Ether is called out as alkane, right? With the carboxy substituent. Okay? So same will apply here as well. You should first locate, right, the alkene, and then this has to the main chain, right? But this we call out as a butane, having the carboxy substituent at number 4, right? And you have number 1 site for the alkene, okay? And this has 1, 2, 3, 4, 5 carbon, so this is a pentoxy substituent. Okay? So you have 4 pentoxy, 1 butane. You can apply the same rule here. The rule we studied for diene. You can locate this 2 arcanic site. This is going to be the diene at the end of the day, and you can identify the main chain containing 5 carbons. It's a pentadiene, right? And you should then think about the direction from left to right, right to left, and then choose the direction. From right to left, you can assign this carbon as number 1, this carbon is number 3. This is going to be then number 4-methyl 1,3. Substituents, same rule actually, right? Stated in alphabetic order, right? So you should put ethyl first, then methyl, right? Bromo first, then chloro. In both directions, give the same number of the functional group. The correct name has the lowest substituent number, right? So you can think about this case either left to right or right to left, right? They will give you the same number for the functional group, which is 4, right? Starting carbon is 4 in the direction, right? In this case, you should choose the direction to give the lowest substituent number. In this case, right to left is the correct way, so that you can put number 2 for the starting, right? Substituent. And then you can assign 5 for this carbon wedge. You can call out 2,5-dimethyl, 4 octane, 4 here indicated, right? The starting for the alkene. You can apply the same rule here: the left to right, right to left in either direction. You can assign 3 for carbon, right? Or for the alkene. Then in this case, you should choose the left to right, so then you can assign the number 2 carbon, you can accommodate the bromo group. Okay. The number is not needed to denote the position of the functional group in the cyclic pole. Okay? So you can think about this cyclic structure, the cyclic alkene, because the alkene, right, has to locate in all cases between C1 and C2. Right? That's why you don't need to call out the position of the molecule in this particular case when you deal with the cyclic alkene. Okay. Same, so you can apply all the rules we discussed to practice with all this. And you can also try to do this for the sake of time. I can give you the number where you can apply the rule that we just studied, okay, and practice. 그래서 우리 한번 쭉 보고 나면 꽤 직관적이라 이해가 바로 되실 것이고 이해가 되시면 꼭 연습을 해서 습득을 하시기 바랍니다. 애매한 경우가 있을 수도 있겠죠. 그 경우에는 룰대로 적용만 하면 애매해지지가 않겠죠. 잘 모르니까 애매한 건데 확실하게 알고 계시면 애매한 일이 없습니다. Okay, that's the nomenclature. And we can discuss maybe a little bit special case or particular site when arcane arise in the structure, right? So you have the binylic carbon, allylic carbon. What is binylic and allylic means here? The binylic carbon is this scheme illustrated. Right? This is the participant carbon actually that formulate arcene. Right? In other words, it's the sp2 carbonic site. Not in the arcene. So in this particular case, you can locate these two carbon as a binylic carbon. What about allylic carbon? As a sitting next to it. Right? It's a carbon adjacent to, in other words, sitting next to the binylic carbon. For instance, this site, you can call that as an allylic site or allylic carbon site. Okay? So that's how you can distinguish binylic versus allylic. Same things, basically, the binylic group. The smallest group that contain binylic carbon, right? So you can then define this as a binylic group, right? This is the smallest group containing binylic carbon, right? And allylic group is the smallest group that contain allylic carbon, right? Allylic carbon is this, right? So the smallest possible group has to be this. So this is the binylic group, and you can use that, right? For lecture in some cases, in the common name in